When does it start? Good question. 9 o'clock. Okay. And do you know where at all? Just Ganei Genesis Lecture Hall for the students. Okay. Right. Oh, really? Uh-huh. So, okay. So so those of us who are staying, for example, at Mishkanot, if there's 10 feet of snow, can probably make it to Van Leer by foot. And here kept. So we were going to, originally the idea was to have a panel discussion among, and there were so many panelists that we were going to have 3 separate panels. Most of the panelists have evaporated. But still some of them are left there by the chairs. Now the other thing we were going to do was we had some of the pioneers of general relativity, Bekenstein, who can't make it, and Veneziano, who is stuck in Tel Aviv, and Michael Green, who is here, and I was going to say a bit about heterotic string, but Michael might be at any moment called out because he wants to get out of here today. So I suggest we begin with some short remarks by Michael Green about the superstring revolution, his personal story, abbreviated. You want to use a microphone? You don't have slides.
I don't have slides, but yeah.
You want to use the blackboard?
Not really, no.
No.
I'm just going to make a few comments.
Okay.
Do I need that?
Yeah.
So I'm going to make a few comments about the evolution of string theory. They're going to be extremely, first of all, they'll be brief comments, and secondly, they will not be nearly as polished as that beautiful talk that you just heard, but that's partly a reflection on the state of the subject. It's a reflection on me, but it's also a reflection on the state of the subject, and I think it's one of the most curious things about string theory is the way it evolved in a seemingly random fashion. It started. So I think my plan is just to give a brief hint as to how the subject started and what happened subsequently. So it began. It grew out of experimental data, but it was experimental data on the strong interactions. There was a period at the end of in the middle and end of the 1960s, at which in the particle physics community, there was a period of frustration with quantum field theory. Quantum field theory, of course, had been enormously successful in the context of quantum electrodynamics, but then attempts to apply it to the other forces, the other non-gravitational forces, seemed to be doomed to failure. And so in certain places, and this, including the place where I grew up in Cambridge, and I believe the place where David grew up in Berkeley, there was an attempt to get away from the constraints of quantum field theory and the program called the S-matrix program was formulated, and this was an attempt to understand the strong force in particular, outside of the context of quantum field theory. I mean, ironically, I suspect that tomorrow you may hear more about attempts to understand the forces by avoiding quantum field theory in its traditional formulation. But anyway, in the past, in the late 60s, this was a program that was very much pursued in certain places. Again, looking back historically, the astonishing thing was that this was the period in which quantum field theory itself was in fact undergoing a revolution. This was the period in which Weinberg and Salam and Glashow and others were formulating the electroweak theory. But in places such as Cambridge, this was ignored. I was doing my PhD in the late 60s, and I was very much under the influence of.
This would be like in The Sounds of Music. You would say your piece and leave.
Okay. I like. We need at least 7 people, don't we? Leave one by one. So anyway, so I was doing my PhD in the late 60s, and the subject, in retrospect, was in fact rather sterile compared to what was happening in quantum field theory, apart from one isolated event, which was the paper by Veneziano. So in 1968, Veneziano, who should be here talking about this himself, produced his paper, which I think, without any doubt, is the paper which marks the beginning of string theory. It wasn't string theory at the time, but it was the paper which led to string theory within a few years. Before Veneziano, there was no such thing, and after Veneziano, there was this formalism. He made a very beautiful and very simple guess for the scattering amplitude of mesons, and this guess led to everything that followed. So I was alerted to this by my supervisor. This was probably the best thing my supervisor ever did for me. Well, okay, I'm happy to say that. I mean, it's true. And then, so rapidly, within a few years, a small group of people had started the enterprise which led to string theory. Ironically, of course, that was also the period in which the standard model was being developed, and the original purpose of string theory, which was to explain hadronic physics, was sort of usurped by David and his colleagues, who formulated the theory of QCD, which became the theory of the strong interactions. So that for many purposes, it seemed that we now had a theory of the strong force. However, that theory, of course, is very curious because it contains quarks and gluons, but these quarks are confined, so that there's no such thing as an isolated physical quark, which led some people, including myself, to believe that there may still be a role for string theory in describing these confined particles, describing mesons or baryons. And what preoccupied me at that time was the question about how one could understand, without having fundamental quarks and gluons, how one could understand that there was this phenomenology of the strong interactions in which there's point-like substructure, and how you can understand that in terms of a string picture, where the string, in some sense, describes the flux tube that joins a quark and antiquark together. So that's sort of the early 70s. There were developments in string theory going on, which was being pioneered by a rather smallish group of people, up to around about 1977, 78. And that group of people got smaller and smaller because I think, well, there are many reasons, but one, there were other things happening in field theory which were so fascinating and so captivating that people prefer to work on that subject rather than string theory. So this was a period in which the standard model had been formulated, monopoles and instantons had been discovered. These are solitonic solutions of quantum field theory of great interest, with a great interaction with the mathematics community at that time, the mathematics of gauge theories. Supersymmetry had emerged and supergravity, and these were all enormous new projects which had taken the attention of many people in the field. And so by about the end of the 70s, there were rather few people, very few people working on string theory. And this is a period where I got together with John Schwartz. We met by accident in CERN. We'd known each other a bit earlier when I had been in Princeton. And we decided that we were going to pursue string theory in its supersymmetric formulation, which was the formulation that appeared to have some great consistency. So, I mean, the message there is sort of peculiar because around about 1977, string theory had finally been, it had been understood how to overcome the most obvious difficulties of string theory. There was a very important paper by Gugliozzi, Shirk, and Olive at that time, but the emphasis in that paper had been how to use string theory to develop theories of supergravity being quantum field theory, rather than to develop string theory itself. And so those authors and others didn't pursue that. So John Schwartz and I got together, and we sort of we understood that supersymmetry was a key ingredient in understanding the mathematical structure of the theory, and so we reformulated the theory in a way that made the supersymmetry manifest. We started doing this in 1979, and we worked together in a period of about 5 years, over a period of 5 years, where there was this extraordinary luxury that very few other people were working in the subject, so we could get together for a couple of months or 4 months, 3 or 4 months a year, and work together, and then separate and get back together a year later, and there would be no other papers on the subject, more or less. I should say, of course, there were, of course, some extremely important papers, but we didn't appreciate their connection with what we were doing. In retrospect, of course, they are hugely significant, the most significant of all probably being the ones by Polyakov, which came out in about 1981, 81, showing how to formulate string theory in a much more geometric manner, which is the manner we now all use when we discuss it. So we, in that period between 79 and 84, reformulated the theory in a way which made the supersymmetry manifest, and that simplified many of the calculations. The calculations we were doing were, again, in retrospect, very elementary, and we were doing them in an extremely complicated manner. But they were quite captivating for us, and in particular, we did a calculation of the scattering amplitude of gravitons at one loop in one of the string theories, and we found that the result is finite. The result of this is a closed string theory. Quantum corrections in closed string theory, these are like perturbation theory corrections. They're the analogues of Feynman diagrams, and they're always ultraviolet finite in string theory. But we didn't appreciate that at the time, and it was of course exciting and interesting to find an explicit quantum loop calculation in gravity that was finite. That was in 1982, and that persuaded us that we were onto something that might be interesting. Many people suspected that if we looked at theories which in some sense at that time seemed more realistic, theories which had gauge symmetry as well as gravity, that we would encounter well-known problems with anomalies. These are chiral anomalies which constitute a breakdown of some of the sacred symmetries in field theory. So, for example, gravitational anomalies, which a breakdown in the conservation of energy momentum. These are problems that would kill the theory, and in our naivety, we didn't appreciate perhaps how significant such problems might be. We just set about calculating the anomalies, and we found that they, in fact, didn't occur in certain theories. So we came up with the statement in 1984 that it was possible to have a theory of gravity coupled to gauge theory, in which the anomalies which are potentially going to kill the theory are absent because of a mechanism which in some sense involves both the gravity and the gauge sectors together. So this is a mechanism which made the theories consistent, but it made it consistent because string theory automatically contains general relativity within it, as well as the gauge sector. So there's this wonderful thing about string theory, that it unifies gauge theory and gravity. But at that point, that was a rather surprising result, I think, to people who were doing conventional quantum field theory, because they weren't thinking in that way, that you should couple the different sectors together. And this is, in some sense, an intrinsically stringy mechanism. So that was in 1984, and at that point, the world sort of changed, because various people, in particular people in Princeton, became very keen on the subject, and there was an explosion of activity involving in particular David Gross and his colleagues in Princeton at the time, and he's going to talk about that. Let me just say a little bit more about what happened next. So what happened next was that the subject rapidly developed with enormous changes. Everything I've mentioned so far has been in the context of what we call string perturbation theory, which is the analog of doing Feynman diagrams for a theory. But it's the analog of doing Feynman diagrams for a theory where you know the Feynman diagrams, but you don't know what do they approximate? So the big question is, how does one generate a non-perturbative formulation of string theory? And it's that which has really been the emphasis of much of the work since then, leading to enormous insights into non-perturbative aspects of the theory. These non-perturbative aspects relate what appear to be very different kinds of theories, kinds of string theories and supergravity theories, to each other by what are known as dualities, and maybe the culmination of those dualities came about through, well, Joe Polchinski discovered D-branes, which are non-perturbative soliton-like objects in the theory, and then with a lot of brilliant insight, there followed the work of Juan Maldacena and Sasha Polyakov and Klebanov and others in understanding that there is a profound duality between gauge theory and gravity. That string theory contains within it, as I've said before, a natural kind of unification of gravity and gauge theory. And one way in which this is manifested is via the gauge-gravity correspondence, which is which you can see explicitly in very specific backgrounds, at least, where you can either describe the theory in what we call the bulk as a theory of gravity, or the string generalization of gravity, or in these particular backgrounds there's a boundary and you can describe the same physics of the bulk in terms of a gauge theory living on the boundary of the bulk of the space. So there's this new principle that has emerged. It was first suggested on more general principles by 't Hooft, but it's become a sacred part of the whole subject now, that we can understand perhaps the physics of string theory by understanding the physics of gauge theory being a non-gravitational theory. And that has somehow promoted a lot of the research in recent times, in particular this connection between gauge theory and gravity has been at the center of, I think, probably a lot of what's been said at this school in the last couple of weeks. It's certainly at the center of the way in which many people are now trying to envisage the emergence of the bulk space-time from the gauge theory. So there's this ongoing enterprise in trying to understand how space-time might emerge, quantum space-time might emerge from physics of what appears to be a very different type, the physics of gauge theory. I've said more than I was asked to say. So.
So, Eliezer,
I think one, of course, is the next.
yes,
We hope. Right. Well, one is more complicated. Let's start.
Are you leaving? We're trying to get you out of here.
Oh, okay.
But if not, you could talk. What?
Yes, one will leave. I suggest leave now. Let's not go over the
Yes, sir. Am I leaving or talking?
You're talking. Just talk 5 minutes and then the next.
Talk 5 minutes.
Yeah, talk 10 minutes.
Say
Okay.
whatever you want.
Okay, it looks like I'm talking then. Okay, so in the previous talk, not Michael's, in the historical talk, we saw that this microphone doesn't work, right? This is for recording? No,
Single speaker at a time. Just use
the paradox with black bodies in the development of quantum theory, or the problem of making Newton's theory consistent with special relativity. And a paradox that has played an important role in the development, recent theoretical developments, is a theoretical paradox, which are the paradoxes involving black holes. So the fact that when you have a black hole, which is a standard solution of general relativity, black holes, as discovered by Hawking, have a temperature which is proportional to 1 over the size of the black hole. And this is a surprising and interesting discovery by Hawking, which relates a bit some properties of general relativity with properties in quantum theory and statistical mechanics. It's again one of these problems which relates different areas of physics, statistical mechanics, quantum mechanics, and gravity. The three are related in a connected way and in a confusing way. So, understanding the origin of this temperature. So we have just naively a vacuum solution of Einstein's equation, and suddenly we get temperature, which is supposed to be due to the microscopic motion. According to statistical physics, is supposed to be due to the microscopic motion of some constituents. And what are the things that are moving? I mean, this is space-time. The atoms of space-time, whatever they are, is the thing that is giving rise to this entropy. And so understanding this problem was, continues to play a very important role, and I think will lead us to develop a better theory. And by the way, so normally we think that this is an effect which has not been measured, and indeed has not been measured in the context of black holes. But essentially the same effect appears in the zeta space and creates the cosmological fluctuations which have been measured. So we can really say that this is an effect which plays an important role in the functioning of our universe. It plays an important role in understanding why the universe is not uniform. So far from being a theoretical curiosity, is an effect. These effects of quantum mechanics and gravity are effects which play a dominant role in understanding what the universe is. And not only that, but it plays an important role in not the microscopic aspects of the universe, but the actually large-scale structure of the universe. So once you understand some of these features, you are relating things which naively are totally unrelated. So, and that's thanks to the theory of inflation. And we hope that once we understand the quantum mechanics of gravity, we might also find that similar relations. So Michael briefly discussed this relationship between gravity and quantum field theory, and this has led a kind of unification between different aspects of field theory and gravity. So we saw that quantum field theory apparently doesn't have a geometric formulation, but certain large-n quantum field theories, so QCD-like theories in the limit of when the number of colors is very large, have a kind of geometric description. So it's a unification with geometry. Also, we think that this notion of geometry is generalized in other theories, so it's a generalization of the notion of geometry. People have found some interesting relationships by looking at fluctuations of black holes between the equations of hydrodynamics and the equations of gravity in very precise ways. So you can get from Einstein's equations to the Navier-Stokes equations, the classical equations of physics. So in some sense, we are starting to see geometry and general relativity in more and more problems. So it becomes useful to think about black holes not only in the context of astrophysics, but perhaps as toy models for problems in condensed matter physics or fluids, strongly interacting fluids, and so on. So that's an important point. And I'd like to finish by saying that we normally think of, thinking about black holes tells us that, again, I said this point that relates quantum mechanics and gravity and geometry in an important way. But it will teach us how quantum mechanics works in gravity. And we are learning that it works in interesting and surprising ways. The picture that, let's say, de Wit and the first people who tried to quantize gravity perturbatively developed is that, well, we have a classical field theory and we have the field, we have the geometry, and then quantum effects affect the geometry at very small distances, right? So it's something that is occurring at very tiny distances, and that's where quantum mechanics plays some important role. So that's that picture. But we now think that there are quantum effects that can
Senior
affect.
freeze this time, you have 3 minutes.
Yeah. So that there are quantum effects that quantum mechanics actually seems to be playing a crucial role in determining what the geometry is and what actually is close by in geometry and so on seems to be related to entanglement. So, and this goes back to the simplest solution in general relativity, which is the Schwarzschild black hole, which in the modern understanding after the Renaissance, we know that it can be completely extended beyond the horizon into this geometry that contains 2 black holes. So this is a geometry which then through Wheeler and so on have shown that can be viewed as there is a small generalization of this geometry where we have 2 black holes separated in the same space-time that are joined through the interior. And we think that the interpretation of this geometry corresponds to 2 black holes whose microstates, the microstates of the black hole are whatever are giving rise to this entropy, are entangled between the 2 black holes, and that the entanglement between the 2 black holes leads to a geometric connection between the 2. So this is saying that this, so whether something is entangled or not is a subtle quantum effect, and we are learning that this entanglement can create geometric connections. So it's not, so this, it's not, we are not talking about a tiny effect, but we are talking about a big geometric effect. Yeah. There was one more thing I wanted to say about this. Okay. Sorry, I think I'm about to finish. Sorry. All this rushing, I mainly forget what I wanted to say.
Sorry.
What? Yeah. So. Oh, yeah. One more point I wanted to say is that for this connection to be consistent, it's important that you cannot send signals through this wormhole. And the fact that you cannot send signals in the gravity description is due to some properties of gravity which are not directly related to quantum mechanics. They are related to positive energy conditions, to singularity theorems, to a whole series of things that people have been studied in the context of general relativity. And that ensures that this interpretation is correct. So on the other hand, from the point of view of quantum mechanics, you cannot send signals due to the fact that they are simply entangled, and entanglement doesn't allow you to send signals. So we're relating some property of quantum mechanics to some property of general relativity. And well, so this is one example in which we see these things. So of course, these are all theoretical explorations, and hopefully in the future we'll understand the theory, but a whole theory which puts in all these things in a complete way. Thank you.
Okay. So actually, I wanted to just make a separately a few comments with respect to your sparking questions. One thing which is might be of interest.
Maybe you take the. Oh, it's here. The microphone is there. One on the chair.
Which might be of interest to you is you talked about the renaissance of relativity and the fact that this community was isolated. There are other examples of that, one of them actually being string theory. So string theory, as Michael explained, began in 1968. Okay, it's been around now for 46 years. But it was a small group of people. Wasn't that small until it grew and then narrowed and then exploded. So there was a renaissance also that John Schwartz and Michael Green were largely responsible for, which hooked on to a different effort that was going on in particle physics and trying to unify using supergravity ideas and so on. And the two came together in '84. But this was also a community that, for example, had no conferences. It took 20 years in string theory before there was an organized conference on string theory or workshops. Most of the community in elementary particle physics totally ignored this field. And in many ways, it was similar to general relativity after the initial burst. There is something, and that's unusual, so-called in science, and certainly in physics. And partly that's due to, which you didn't bring up, but is due to the fact that these are both fields which are totally divorced from experiment. Most of theoretical physics is an attachment to a large part of physics which is experimentally driven and is doing experiments all the time, making observations, discovery, needing theorists to construct models to interpret their data, and so on and so on. That's what most of science is, most of physics is. But in physics, we also have these areas which largely are theoretically driven, and therefore they don't get financial support from the big money that goes into experiment. That was certainly true of string theory in its early days. Now it's at the forefront of theoretical physics, so it's well supported compared to what it was in those days. It's a pity that Michael isn't here because he was he claims to have run the first string workshop ever, which spent half of its budget to bring me from Paris to London on a cheap flight. In 1983, when I was visiting my friend André Neveu, or I went there to Paris to get back into string theory. I thought, and Mike ran a workshop actually on string theory. That was 1983, which was 15 years after the field began. There'd never been really a workshop conference devoted to what? It's quite kind of amazing. And it's sort of similar to the way you discuss history of general relativity, which was another example I think I just thought of, but I'm not sure it's that, is quantum information theory. Until recently, it was also in the bylaws, very few people doing it, very little support, and then suddenly it exploded because of its connection to nanotechnology and so on. The resurgence of general relativity after the war, or of string theory in the mid-'80s, is more of a theoretical resurgence, right, in both cases. Although in the case of general relativity, there were also astrophysical. Yeah. So I just wanted to bring up that remark. We also have actually time for people to question you or to discuss your otherwise brilliant, lecture. Or we could have some comments like Juan giving some picture of how we think now of general relativity. In my opinion, one thing that hasn't been stressed towards the end of your presentation is the big change that occurred in our understanding of our framework for theoretical physics, quantum physics, relativistic quantum physics in the 70s within the particle physics community. So, which explains to some extent the answer to one of your initial questions. Why was general relativity so successful? So our understanding of changed dramatically with we could call the Wilsonian revolution. The way we think about writing down the laws of physics, the way we think about formulating the fundamental laws of nature. Used to be, and certainly Einstein's motivation, goal, which he convinced many of us is a worthy goal, was to find equations that would describe all of physics, or at least some aspect of physics without any limitation. And if there was a limitation, there was a sign that you had to change the theory. But after Wilson's insight into the structure of quantum field theory, we realized that that goal is sort of unphysical, is not the way we really do physics, one, and that the theories we possess, including general relativity, are at best successful effective field theories, we call them, which means they're constructed to describe a certain range of energies, distances, and have no reason to be valid beyond that. And that change of view, which happened quite rapidly, I would say over a period of 10 years in the 70s, really changed the way we think about a lot of things, but explained a lot as well. So for example, it does explain why general relativity is so successful. So we change the point of view that general relativity has no chance of being a final theory of gravity. There's no reason for it. Following Einstein's logic, there's zillions of theories you could write down, all of which are equally good. But because of the whatever reason, the disparity of scales of distance and energy between the so-called Planck scale, the scale in which gravity is a strong force, and our scale, atomic scale, nuclear scale, of many orders of magnitude, 20 orders of magnitude. Einstein's theory is sort of the only theory that's possible with corrections that are clearly immeasurable. From that point of view, there's an answer to your question, which doesn't lie in sociology or anything. It simply lies in the way nature is constructed. We also then realize that, there's going to be some alternative. There's no reason why not. Some change when we get to the scale of energy, the Planck scale, and we have no idea what it is. It could have been an ordinary quantum field theory, and in fact, there are proposals. Weinberg pursued an idea of so-called asymptotic safety. It would have been a sensible ultraviolet, we would say, corrections to Einstein's equations, which wouldn't have been revolutionary. Personally, because of the many other issues aside from just this renormalization or the change of the physics with scale, never had much attraction to me. And I don't think it's the case, but it's logically possible. From other considerations, like black holes and other things, and most importantly, unification of the forces, we have been pushed, therefore, to string theory. Loop quantum gravity, by the way, is a totally different kind of approach, whatever it is. It's a technical, in my opinion, we have representatives here who can argue. It shouldn't be, in my opinion, but this is the purpose of having a discussion, matched against something like string theory. Now, Michael explained how string theory came out of experiment, nuclear force, etc. There's a good reason for that in the content of what we now understand these dualities, which realize that correspondence between mesons as flux tubes and fundamental strings. Ed Witten once said that the most remarkable prediction of string theory was the existence of gravity. And in a conceptual sense, that's correct. String theory, as we view it now, with this gauge string duality, ADS, CFT, etc., gives us a representation of gravity as in terms of relativistic quantum gauge theories that we understand better. And we're using that. I mean, a good part of this school was devoted to exploring that topic. And it's so in a sense, what Ed's remark was that conceptually, if we had never known about gravity. Perfectly possible in some weird world. We still know about the other forces of nature. They're very strong. They determine the structure of matter, everything we see around us. We could have discovered from either the original perturbative string theory or the more sophisticated gauge string duality, dynamical spacetime. Loop quantum gravity is a totally different kind of approach. It's more a interesting, clever, imaginative way of trying to quantize Einstein's theory. Okay? Very different than our approach, which is, they said, Einstein's theory is not sacred. The principles are sacred. Einstein's theory is an effective field theory, valid at low energies. So that's the comment I wanted to make on your thing. And others can add to this. We have Joe here and Nima, who might, these are people who are working at the frontier, what they think about the future of general relativity.
David, are you going to give me a few minutes to say something?
I'm not the, sure. Do you want to wait till?
Whenever.
Comment about what you said. I mean,
Yeah.
Not about the future.
But do come up. And Joe, do you want to?
Sure.
Yeah. After Nima?
It was really just a
You
comment.
can
just
also-
following immediately on what you said. So I think one other thing. Oh, okay. Fine.
have a panel.
Panel. Yeah, I just had a fairly a follow-on onto what David was saying. I think something else that we started appreciating a lot better in the 1960s and 70s, and I think it's another one of the quiet revolutions, along with the Wilsonian picture of the world that David mentioned, is that there's an extreme amount of what Steve Weinberg calls inevitability in the structure of the laws of nature, at least as we see them at low energies, that follows from consistency with relativity and quantum mechanics. This is a really amazing thing. If we only knew about the laws of relativity, there would be an incredible variety of possible theories we could use to describe the world. If we only knew about quantum mechanics, enormous variety of possibilities we could use to describe the world. But we know about both of them, and all of a sudden, it's tremendously constrained. I mean, it's a sea change compared to everything which came before. I like to say that if you handed the laws of relativity and quantum mechanics to a group of sufficiently competent theoretical physicists, locked them up in a room, refused them to look at what the world looked like around them, they have to be sufficiently competent. If you gave them to me, if God gave me the laws and said, go, build a universe compatible with these rules, I'd say I can't do it. Okay, I can't do it because the kinematical frameworks of the two subjects are different. Quantum mechanics changes everything, but it still has time. Time is very important. You specify the state of a system at one time. You have to evolve to another time. Relativity says, just special relativity says you're not allowed to think that way and so on. It's not at all obvious that they're compatible. But if you hand them to sufficiently competent theoretical physicists, then from that point on, from pure thought, you could work out what the world can possibly look like at long distances. And you find that there's a tiny menu of possibilities. If you have interacting massless particles, and we take the approximation where they're massless because very high energy, very short distance physics, very high energy physics, you'd be able to ignore the masses of the particles. So when the particles are massless, you can just mathematically work out what the allowed possible interactions are. And you find that you can only have massless particles of spin 0, 1/2, 1, 3/2, and 2. You can't have particles of spin 17 halves, and that spin 2 guy is unique. And you work out its properties. You can't have two of them. You can only have one of them. And you work out what it does. It makes things go around in orbits and stuff like that. So it's gravity, of course. But there's no falling elevators. There's no beauty of curved space-time. There's no general covariance. There's no beauty of gate symmetry and geometry that goes along with that when it comes to describing Yang-Mills fields. Those are all sort of human mental constructs that help us understand this unique, consistent possibility for how these things interact with each other. I think this is an extraordinary thing. And related to that is that there are rules. It's been emphasized that this is a very theoretical subject, but there are sharp rules. If someone comes along and tells you they have a theory of quantum gravity, there's many things such a theory should do, but very minimally it should answer some very simple questions, like if you scatter two gravitons at each other coming from infinity with some energy at some angle, and they come back out some energy at some angle, what is the amplitude for that to happen? And it has to give you a formula. There's got to be an actual concrete formula where the probabilities add up to 1 and it's compatible with relativity and compatible with the relativity. If you make very simple assumptions about what that formula can look like, if you assume that there is a weak coupling, so this amplitude never gets very large, then in the 50 years that people have been even imagining about doing an exercise like this, there's only been one formula that's been found that's compatible with these. That formula is called the Virasoro-Shapiro amplitude, and it tells you about string theory. And it's fascinating if you just try to mess around with it, even in tiny ways. It breaks. It immediately breaks one rule or the other. So it's not a question of sociology. If tomorrow one of you in the audience comes up with another formula has the same rules and performs the same miracles, then it'll be spectacular. But no one has come up with one. And so yeah.
That's great. However, there is a lucky circumstance that it forms one of the big puzzles that we're still coping with, which is the disparity of scales. So if the scale disparity had been much lower, it would be much easier on the one hand to understand the dynamical space-time or gravity or whatever, and on the other hand, impossible, as you know. So it's not, you're discussing a perturbative-ish approach.
Yes, yeah.
So we're going to start running out of time, so let's let other people speak.
So I first had a couple comments on the very nice talk, and the first one, actually, the robustness of GR has been really beautifully handled by David and Nima. And also the robustness partly comes from the smallness of the Planck scale, 10 to the minus 33 centimeters, the place where non-renormalizability kicks in. I think your first historic point in quantum gravity was Bronstein, but it's always worth remembering Planck. Because Planck, in 1899, the year before the official discovery of the radiation formula, knew he had this new constant, and he showed that he could combine h bar, c, and g in a unique way to get a length. And it's pretty funny, because h bar, c, and g are the three constants that kicked off the revolutions of quantum mechanics, special relativity, and general relativity, and already in 1899 he had identified these as the constants that were so important. And actually, he was beaten by 25 years by George Stoney, who didn't know about Planck's constant, but he inferred from Avogadro's constant that electric charge should be quantized. So he used electric charge instead of h bar. So Planck's calculation was the second calculation in quantum gravity, and Stoney's was the first. So that's just a historical bit that I think that I really enjoy sharing. As far as the future, so Mike Green mentioned this random walk, and it's worth noting that strings themselves are just one stop on this random walk that we've moved on from. After strings did all their wonderful things, it was natural to try to build a complete theory on the basis of these one-dimensional structures, and you know, basically these directions were sniffed out and hadn't been so fruitful. And now with gauge gravity duality and ADS-CFT, the strings themselves are just emergent in some classical limits and not others. They're as are particles. As are gravity, space-time, and the equivalence principle and coordinate variance. So it's the funny thing about a random walk. I mean, random walk is a funny metaphor, but it's very accurate. I think it incorporates two things. With a random walk, each individual step is very unexpected, but not necessarily so long. And that's partly because again, the physics that we know so much about physics, it's so constrained that we need to incorporate the knowledge we already have. That's why the steps are not so long. But empirically also, it's not an easy course, and at each of these random steps, we have to sniff out many directions to find the next. And so, you know, it's you can't make a lot of, well, you can make a lot of money convincing other people you know where a random walk is going, but you can't make a lot of money actually predicting it yourself. And so I don't know where the next step is going, but I can, you know, tell you what we're now sniffing out. And it's what Juan touched on. I mean, non-renormalizability is one of the paradoxes of combining gravity and quantum mechanics. The black holes present many others where the two theories point in different directions. And this has led to notions of holography where locality, even locality, another thing that is not is no longer necessarily fundamental, is something which emerges from much less fundamental building blocks. And what's really interesting today, and Juan alluded to it, is that up until now, all of our theories have lived in the framework of quantum mechanics, quantum field theory, string theory. They've lived within this framework, but they haven't challenged it so much. And now the ideas we're talking about seem to be even challenging that framework. Maybe this will be wrong. Again, we're sniffing out directions, and we're going to take a random step sometime in the future. And it might, in fact, I think there's a broad feeling that it will unite quantum mechanics and space-time in a really interesting new way. Thank you.
Let's continue with remarks of people on the stage, and then we'll have maybe some discussion or questions. But let's give everyone a chance.
Okay, so running around in the last few days and trying at the same time to solve the deep problems of the universe brings me back to the human aspect of in this adventure we are engaged in. And I'd like to say some things from that point of view. I would say some things which were for me magic and when they happened, and they motivated me to go on and pursue. And then I will dare, in also a very short comment, a little bit into your history, and I will talk about revolutions and tools for revolution in our field. So the first thing, as I grow, the older I grow, I marvel at how it seems that the human being can impose its will on the nature which is around it. In what way? Well, not in the snowstorm, but, for example, we cherish some principles. We have taste. We heard from Jorgen a lot about principles. We believe in principles, and in general, why should that lead us anywhere? And it does lead us. We believe that symmetry is important. It's symmetry, it's breaking. It seems to be successful. We want certain symmetries like gauge symmetries. We use them, and then we are at a stage actually where many people would call them redundant and would like to dispose of them. We move in space-time. It's very firm. And then we want to say, actually, all that's an illusion of our human mind. Actually, what is going on here is much more complicated. But our desire to put things, articulate things into laws which are compact seems to work, and it seems to work for most of the time. And I marvel at why this happens. I see no reason that it should have happened unless we're imagining things. But it doesn't seem to me that we're imagining things. Then from the point of view of magic. So one magic was when Wilczek Pulitzer had a well-defined field theory. When I was a student here, I was told that the only field theory which exists is free. And this was proven rigorously, or in Harvard or in Princeton, I forgot where, and it was not possible to have anything but free field theory. And once asymptotic free theories came out, it was clear that that is not the case. So that was weak coupling, and then it was obvious we'll never be able to do strong coupling. And now it's not easy, but we are also able to do field theories in strong coupling in physical dimension 4. And not only, but it is related in some way to general relativity. So that is one more magic which happened. Another magic happened to me in this hall when Stephen Hawking gave a talk about the Wheeler. I didn't know before about, I'm ashamed to admit, I didn't know about the Wheeler-DeWitt equation before 1980. He gave a talk here, and when I heard about struggling with ideas of what is a wave function of the universe, it touched me, made me very excited. And I think it was my first touch with, if I like it or not, a landscape, because the moment we accepted the Wheeler-DeWitt equation, we had no criteria on how to choose between the different solutions, or at least if there is a criteria, we didn't know it at that time, and that was a challenge. And another magic I see on a daily life is the many narratives or many dualities which we have, which tell us that we can describe in totally different way once string theory is involved, or once extended objects emerge in some phases at least, we can, all the concepts we know in mathematics become ambiguous. I won't now enter into to detail it, but I challenge you, give me a concept in mathematics except the value of pi, and I will show you that actually there are two different narratives to describe that. I will end up with a comment on the sociology, which is very superficial, but I'll say it, I'll use the fact that you are here so I can say it. So it is very important here as a students, the vitality of the field comes from the new ideas and the new people. Now, as you know, physics generically is a benevolent dictatorship. Namely, people are very strict, but the moment you come with a revolutionary idea, even if nobody liked it, but you can prove that it has to be, it's related in some way, mostly to nature, then you have to accept it. And not only do you accept it, but usually you put the person next to you on the executive committee. So it's not so easy to, it's not so easy to make a revolution, okay? That was, no comment on that. So it's really very difficult to do it. So what do you do when you're not really tied to nature, as we are in string theory? Unfortunately, it's not our fault. Gravity seems to be. Our dreams that it's a sub-micron don't seem to be borne out, at least till now. So it doesn't seem to be so well matched with the human scale. So here we go to Einstein tools of consistency, symmetries, okay, which may mislead us, but these are the tools that we have. So Michael Green described to you the very complicated way they did things. When Schwartz and Green did their work, it wasn't easy to read and not easy to understand for most of the people in the field. Then when the new generation came, they used a different tool, two-dimensional conformal field theory, which Michael hinted when he talked about Polyakov. Then a next revolution, in a way, was needed, another change of guard. So then came in Joe with D-branes. And then the consequences of D-branes, in a rather smooth way, came together with Juan and the ideas of holography. And I think now, I feel the younger generation trying to take some stake in leadership, is trying to contact these ideas of entanglement, quantum information, breaking codes or preserving codes. And this is a language they're developing, and if it will be successful, they will be sitting here. These are my comments. I will be sitting down, listening. Yeah.
Okay, now, before we go to questions or discussion, I need to let Carlo respond to my remarks about.
It's going to be very brief, very
Absolutely. Good.
very short, but mostly I want to talk to the students. First of all, many of the students don't know me. I'm Carlo Rovelli, and I'm a little bit of an outsider here in the sense that I am pretty far from the string community. So the first message I'm giving to the students is that there are other communities. That's very simply. There's a large loop community with conference and a lot of ideas and a lot of very strong conviction, and people say, yes, it's that, look, which are alternative to the ones you hear here. So unfortunately, there is a little bit, or fortunately, because I think debate is good in science, there is science go ahead because there are different ideas and there is discussion. Then things get clarified with the time. But unfortunately, there is a little bit of strong distrust between the two worlds. I tell my students, I'm happy with my students go to string conferences, They go, they try to, I tell them, look for yourself. Let me just say one thing. The people sitting here, I believe, are all people who didn't do what their teachers told them to do, did something else. Went their own way, read the book, go to where they were not supposed to go, and came up with their own way of thinking. Having said that, there's no sense at all in which I see hear myself as alternative to David. I want to stress that. There's a huge difference. David has understood the strong interactions. I have an enormous scientific respect for David because I think he's one of the few people who has made a deep, substantial step ahead in understanding nature. Can I exaggerate a little bit? I view David like
You're just
Einstein.
making it impossible for me to attack.
No. You will, because there is a continuation. I view David like Einstein a little bit, really like Einstein. He did fantastic work in his young age.
Okay, so now the
and then got lost in the dream of a complete theory of. Sorry, that was a joke. But no, but there's a point here. The point here is that I think there's a message to this young students which we don't give enough. It's important to distinguish established theories that have made their proof, not because they're final theories, of course, we don't have final theories, but because they've worked. And QCD is one. QCD has worked fantastically well. That's why he's a real scientist. I mean, and generativity is a theory that has worked, okay? From theories that how beautiful they could be, how convincing that they'd be, how coherent they could be, they haven't given a single indication. And the theory I'm working on, loop quantum gravity, is the second kind. So I work on a theory that I like and love, but might be wrong, okay? It may be factually wrong, but it'd be interesting or whatever, but might have some predictions which are actually wrong. And string theory is the same. It might be wrong. And I think we should keep this clearly in mind, that there are open problems. Quantum gravity is a problem. Unification is a problem, is a different problem. And here I totally agree with him. Loop quantum gravity focuses on solving the question that Nima so clearly said, is so difficult to have a coherent scheme that is consistent with what we know about general relativity. I'm not making ideological things about background dependence, I think, just with and coherent with quantum mechanics. It's extremely difficult. So quantum gravity is an attempt to describe the things that Juan called the atoms of space, the structure of space-time at the Planck scale, in a coherent way, forgetting unification, with the hypothesis that you understand one thing at a time. String theory is mostly focused on unification, and quantum gravity as a possibly beautiful outcome of the. I view this as interesting, wonderful attempts, far from having been established in any possible way. Now, how do we establish things? By looking, and I conclude here, by looking what nature talks about. And I want to make a last super short remark. Read the books, read the papers, listen to all the old vanishing guy like us are saying, which is soon gone, you will be the ones who do that. And listen to nature, of course, right? That's science. And nature rarely speaks clearly. It happens sometimes, like SU5, boom. But usually it speaks in a sort of clear way. Recently, nature has spoken very strongly, okay? And there was a community of people who was completely sure that it would have said one thing, and nature said the opposite thing, okay? There was a community of people, I'm sure none of the people here belong to that community of people, but a large community of people who were absolutely sure that as soon as LHC was turned on, supersymmetric particle would have appeared, okay? Now, of course, what do we know? It's perfectly possible that now LHC will be turned on again, and supersymmetric particle would appear. But I remember being at CERN a few months before, and my very good friends, supersymmetry guy, supergravity guy, string guy, telling me, Carlo is completely sure. I mean, supersymmetry has to appear as soon as we take LHC wrong. They were all
You have recordings of it.
Yes, I have a recording. I can give names if you want, with dates and record. Yeah, no, but people are honest, and you can ask them. I don't think people hide that. They were wrong. Okay, they may be simply they were wrong because supersymmetry is not here or there. Perfectly possible, but they were wrong. Okay, and I think nature talks, and we have to listen. That's all.
Okay, before I unleash Nima, I would like to know whether there are comments, questions from the audience. Or anyone else who wants to express a point of view? Yeah.
Where's the boundary between physics and philosophy here?
On this stage?
Experiments. Experiments.
Inside each of us.
Personally, I'm really sad that philosophers and physicists don't have more of a really useful conversation today as they did 100 years ago. I have a feeling it's because physics has become more technical and harder, so it really takes an enormous amount of effort just to be able to understand, to be at the forefront of physics, as well as to be interested in philosophical questions. But it's unfortunate, in my opinion. Philosophers played an important role in 100 years ago. Look at Einstein and Mach. So we don't anymore, by and large, as far as I can see. Jürgen?
Just a short remark. Of course, yeah, okay. I won't pronounce myself on the future, obviously, but I want to make two short remarks. What we have been trying to lay out was, of course, not just a sociological view. We have tried really to cope with some of the epistemological problems. So, also the stability problem was not conceived just as a sociological. The stability problem of GR. Why is it? Why has it survived? And I take very much also your hint at the Wilsonian reflection on it, that this is an effect to be considered as an effective theory. This is really an important point that I will integrate. The other remark I wanted to emphasize is a bit on the loop string story. Because you objected to comparing the two or putting them on the same level. And in defense of that view, I would argue, and maybe my co-authors might join me there, is that what is common to these approaches is that they have become much more imaginatory on the fundamental structures. Whereas in the early days, imaginative about the fundamental structure, because as we try to emphasize, oh, surely, that was the message. That was exactly the message that we wanted to convey. In the old days, people were not, trying to imaginatively go beyond the space-times that were known, the space-time as described by GR, trying to impose procedures, like quantization procedures, on them, trying, just to infer from this application what they might be like. And I think, both string theory and loop quantum gravity, to some extent, have turned that around and have become, in very different ways, become more radical, more speculative about what fundamental structures might look like.
But before, but I was trying to indicate that, in fact, string theory, didn't do that. It didn't start out to trying to understand.
No, it's clear, very clear.
It just happened to get there because of this duality, if you want. Started trying to understand the nuclear flux tubes. So it ended up there. Gravity emerged. And as Juan was hinting at, we now, one of the main thrusts of current studies is that there's a quantum mechanical framework which knows nothing about space-time itself or the dynamics of space-time, which will emerge from it, from its quantum properties. Quite a different kind of thing. Anyway, do you want to defend the people, the supersymmetry people?
Oh, no. No, actually, I just had three quick comments. First, on very slightly amplifying what I said before. we all know that the relevant scales associated with gravity are very far away, and so it's unlikely that we're going to have any direct experimental tests of what's going on near the Planck scale. But that emphatically does not mean that there's a sort of a 0-1 binary choice between whether ideas are right or wrong. Okay, that's a very facile view of the way science works. Is that you have a set of we teach it to kids in grade 7, right? That you have hypotheses about the way the world works, and then you compare them to experiment, and you reject the right ones and throw away the wrong ones. Of course, real life there's always a gray scale, because at any given moment today, there's some experiment somewhere that's conflicting with the standard model of particle physics. We know experiments are wrong a lot, and so on and so forth. So there's always a gray scale. We all know that. But associated with that, the rigidity I was talking about before means that even before we get to the point where we can ask whether the ideas are actually realized in nature, there's a very high bar for it to pass, for it to even possibly be consistent with nature. And that is something which is not up to sociology. That is something which can be decided. And we don't, it's not our universe, but many of the same questions about quantum mechanics and gravity which show up in other universes, which are not in detail like ours, but maybe it look like anti-de Sitter spaces, or maybe it look like 10-dimensional flat spaces with supersymmetry, all kinds of stuff that isn't there in our universe, but where you could ask exactly the same questions in that world. And in that world, the answer that we get from string theory is robust, and you can check it's right. So that's a very high bar. That is a very, very high bar. And so it's not just a question of whether things are realized in nature or not.
And as Jürgen, please intervene, as Jürgen emphasized, changes in the fundamental structure of laws of physics are not, Kuhnian revolutions, but the past is gone. They contain it. And when you're in this incredibly speculative domain that we are in, with little experimental guide and heavy hand, consistency with everything we know and is well tested is so crucial. And what we have been asking of our loopy friends for years is to show us how apples fall and the moon goes around the earth. And you haven't yet succeeded. I think there would be less of a rift here.
No, this is not true. I mean, do you know the literature? Do you read the literature? No, you don't. So I mean, come to the conference and listen. There are plenty of papers that derive the classical limit in some. Certainly, we're not being able to do what Nima says. So to come up with
that's the acid test, right? Because everything else, you know the answer beforehand. But,
yeah, it's an acid test that nobody has succeeded so far, because nobody has succeeded in 4 dimensions to do the acid test. I agree.
Well, but in anyway, that's what I said.
Yeah, a little bit there, a little bit there.
But
we have the classical limit in 4 dimensions. You have the full thing in 10 dimensions. Very well. So that's the students here.
Well, anyway, I don't think that's.
Okay.
I don't agree with that, but
the problem is open. The problem is open, and there are incomplete tentative solution. I agree that I don't want to contradict you on the fact that there is incompleteness in loop quantum gravity. Of course there is. I mean,
Carl, perhaps I can ask a question like this. Forget about any actual analytic calculation or anything like that. If this is all, if everything works, you should just be able to take the theory that you have and just put it on a computer. Simulate. Just figure out what it actually predicts and what it does.
I'm doing the code crashes as j equal 4/2 or 4.
Well, okay.
It's too complicated. I could turn the question. Right? If you have why don't you be able to compute the parameters of the standard model? I mean, it's just because it's too complicated. Because I don't know. The theory is complicated,
but
of course.
You're comparing apples and you're really comparing apples and oranges there. You see, we're not trying to decide whether they're computing the parameters of the standard model is going much further for actual realistic theory with the things that we see around us actually matching the world. You're not even trying to do that either, right? You're just trying to come up with something that consistently gives you gravitons or something like that. Anyway, so I think
The status is that we
but it's
do
also-
get
it's
the
also
classical
questioning what-
theory. If we try to compute the quantum corrections,
But I
it's-
think
it's
that's
big
really-
integrals,
that's
huge
really-
integrals.
That's really the acid test is whether it's the acid test is either to present an actual formula which does the mirror. You see, when you look at the way that an actual formula for a 2-to-2 graviton scattering amplitude, really simple, right? Really simple, beautiful formula. When you look at what that formula looks like in string theory, it's such an absolute miracle that it works. It's an absolute stupendous miracle. You take this thing, you expand it out, you see that it has all these incredible properties that make it consistent with unitarity. You try to monkey with it a little bit, it crashes completely. So there's such an incredible miracle in how it works. If you could either find another formula like that, or even give an algorithm that would produce a formula like that you could prove would be compatible with quantum mechanics and relativity, would be done. Would be done this part of the discussion. I think that the reason for this tension is not sociological and is not at least from my and I'm saying it is not because we don't agree with experiment. It's because of a question of the sort of standard of theoretical proof. And
I think that we're going to look foolish in front of the students if each of us says, look, my children, how is beautiful here. Look, my children, how is beautiful here. This is completely astonishing, this particular part of the theory that you don't have on your side. Sure, I mean, that's not the point, I think, of the game. We are not trying to decide here who is right and who is wrong.
We've had we're not going to resolve this, so let's...
But can I just say just two more very quick things? One of them was about the supersymmetry comment. I don't know who you were talking to. It's certainly true that there is a group of theorists who have been saying for 20 years that 6 months from now supersymmetry is going to be discovered as a time translationally invariant statement. Okay? However, it is not true that the results from the LHC are a big surprise to people. They're certainly not a big surprise to me. And the reason is very simple. In many ways, the most natural version of supersymmetric theory should have been discovered in the early 1990s at CERN. In fact, the fact that it wasn't discovered right around then was already a source for some disquiet. And that disquiet was growing, not just, I mean, I'm far from, the generation of people of my advisor started realizing this. It was something that was called the LEP paradox by many of us who worked in this field for a while. And so much so that a number of us even made proposals for theories that dramatically undercut some of the logic for why we'd expect supersymmetry at the LHC already in 2003, 2004, 2005. So there are many dogs that have not barked for a long time. We could have seen rare effects from the presence of superpartners virtually, which weren't seen, and so on. It just was not obvious what the implications of those things were. They're not very dramatic. They were just a source of disquiet. I think, to me, the results from the LHC so far are not particularly more. When people ask, "Am I worried about whether there's low energy supersymmetry there?" I say I'm not more worried about it now after the LHC because I was already a little worried about it before. That will change dramatically if in this next run of the LHC we don't see low energy supersymmetry. Then we'll have indication. Then we'll have indication. No, as I said, this is something not just me, but many people have been saying for 10, 15 years before the LHC. But then what I'm saying is an invariant statement, not about feelings. If we don't see not just supersymmetry, but any natural new physics at the LHC, then we'll be in territory that's definitely pushing us beyond what we are already being indirectly pushed to by the absence of hints for new physics.
Can I say something?
Yes.
To change the subject. And to say something from...
You need a mic.
I was listening to you from a philosopher's perspective, on the one hand, the inevitability of the laws of nature. And this is something that people in science have believed in for a very long time. But then, from what Eliezer said, there was also the message of the equivalent descriptions, the equivalent narratives. This is something that in the folklore is very typical of string theory, and I was happy that it's also on the professional level, a lesson that you draw from string theory, and it's a lesson that is there at the foundations of general relativity with a principle of equivalence, because actually it all started from Einstein's insight into the possibility of two different and equivalent descriptions. So for me, it was very important that together you are giving us this dual message of inevitability, but a plurality of descriptions. Thank you.
There is a young question.
Yeah.
The wait is coming.
Well, he's young enough to run
is
down.
it? Oh, no, it's not coming. No, it's not coming.
Thanks. This is a question for Carlo, and it's not about beauty or miracles. It's a question about experimental science. So my question is, how does loop quantum gravity deal with the very detailed, observation of Lorentz invariance at low energies, and the effectiveness of effective field theory at describing our universe up to higher energies?
The question is about observation or about the theory?
Yeah, it's about fundamental Lorentz invariance.
Oh, the theory is Lorentz invariant. The theory is locally Lorentz invariant, like general relativity. This is a property of the theory. In fact, I think there is a little bit wrong idea that Planck scale is completely inaccessible to observations. This is wrong. I mean, there are conferences about observations in some specific cases. Of course, we don't know scattering at the Planck scale. But about 10 years ago, it was suggested, for instance, that according to some quantum gravity theories, Lorentz invariance is violated at high energy. This has sparked a big observational work with gamma radio burst, with Crab nebula, and so on and so forth. And now, this has been ruled out. So in a precise sense, that particular Planck scale phenomena has been observed, the observation which go at the Planck scale. If you think it's not surprising, because I said SU5, it was ruled out by proton decay, which is a phenomenon at a scale which is just below scale. So in some cases, we can measure things at that scale. So the answer is simple. The theory is Lorentz invariant. It predicts Lorentz invariance. So far, there's nothing interesting to say beyond that, like string theory. Recently, there is a suggestion.
Could I ask for clarification? Because you said some theories predict Lorentz invariance, but loop quantum gravity breaking, but loop quantum gravity does not. I understood
the opposite.
No, you said that some theories predicted it's broken; those
That's
are
right.
ruled out. But loop quantum gravity predicts it's not broken. I think very clearly the opposite has been stated. That it's been stated as a prediction of loop quantum gravity that Lorentz invariance is broken. For example, a recent paper by Pullen and Gambini, many papers, but yeah.
There were some papers that suggested that you can have a state, a specific state that breaks Lorentz invariance. I mean, we have papers, Speziale and myself, much before the saying, wait a moment, I mean, the theory is Lorentz invariant. Doesn't matter what was said. Right now, the theory, there are the equations, you can write down the equations, and they are Lorentz invariant. But I want to make a point. There is a recent suggestion.
Can I say just one quick thing about your comment that you could the problem with these probes of Lorentz invariance from Planck suppressed operators, as I'm sure you know, is that they're very testable. They're so testable they're all dead already, because you can't just violate Lorentz invariance at the level of higher dimension operators without infecting everything else. There's no reason why speeds of light aren't the same and so on. So that's, I think, one of the absolute deepest lessons we've learned about is that. And yeah, so
I agree. No,
that was the comment.
Yeah, I fully agree. But it's still good to test nature and see what nature agrees with our construction. No, I just wanted to say that there is a, but maybe this is out of place. There is a recent suggestion of of quantum gravitational disruption of a black hole in a time shorter than the Hawking time, and the possibility of observing these in fact, possibility of fast radio burst, which is radio signals, which have been observed, might be connected to that. It's very speculative. It might be wrong, of course. But just to say that I think the community of people that call themselves for quantum gravity phenomenology, who try to establish it, would not be surprised if in a small period something astrophysical could come out with some observation which in some way or the other depend on Planck scale phenomena.
Yeah, well, okay. You know, within, say, string theory, we have very well established possibilities where we could observe Planck scale physics, which have also been ruled out. For example, one which Joe worked a lot on was strings, cosmic strings that would be stretched out by inflation and go across the galaxies. It would be a window to Planck scale physics, which could have been there, might still be there at a low level, and would be fantastic laboratories. Years ago, I hoped that we would have enough magnetic monopoles, or around terrestrial, that we could construct a monopole, anti-monopole laboratory and do physics, one event a week at the Planck scale directly. So there are lots of logical possibilities, and I'm sure we haven't thought of all of them, and some of them might still appear. But these are wild hopes. What Nima was saying was that we're in a field where these wild hopes have very small probabilities. We have to proceed with whatever we have to use theoretical tools to guide us. And in string theory, which personally I regard, I describe string theory now, I say we don't have a string theory, and it's not different really than quantum field theory. These dualities relate the two, express one in terms of the other. We don't know where the dividing line is. What we call now string theory is as connected to reality as any other part of our theoretical framework. It's well tested because some of the dual formulations are kissing cousins of, say, QCD. And in fact, we use string theory, quantum gravity, to do at least qualitative calculations of properties of quarks and gluons, quark-gluon plasma. So, if that connection didn't work, and there was something in the structure of gauge theories, the standard model, that contradicted that connection, that we could regard now as experimental evidence against, the whole thing. So it's really very different than the other approach. I wanted to actually ask the philosophers and historians about a book which I wrote a blurb for. That's all right.
How good is it going to get, Jackie?
You got it? That's all right. Don't worry.
I think I'll move it to another room.
No, it's dead.
I don't know why it's doing this.
Okay.
Just go off.
It might have been a message to me. But there's this book which I was asked to review for Cambridge University Press, and I liked it so much I agreed to write a blurb. And I've used it to encourage young string theorists, which is by DeWitt. You must know this book. It's called, what's it, String Theory?
String Theory and the Scientific Method.
String Theory and the Scientific Method. You don't know this book? Richard DeWitt?
David, yeah.
Yes.
I know him, but I haven't really read the book though.
Really? So none of the
I have.
philosophers historians.
I-
You're not. You're a physicist. I'm asking the philosophers or historians and what they think about it. I found it an absolutely fascinating attempt on the part of a historian or a philosopher who's had a background in quantum filter and so on, seems to know a lot about the field. Yeah, I understand. I'm just trying to explain my understanding, to explain how this community, there's a large community of people who are doing string theory, which look a bit weird, perhaps according to the Popperian standard model of how science works. Why are these people, they seem to be intelligent, why are they behaving the way they're behaving? And he has a theory. I mean, he has an explanation, which has a few points. One of them is the point that Nima was making of what he calls overdeterminism. You know, what we know is so elaborate and so well tested, and so that it narrows the possibilities of what can go beyond. Anyway, I found it a very fascinating book, and I was really hoping to hear some discussion of that. I'm surprised that no one. What do you?
I think that one problem with David's book, even though I think it's great that philosophers of physics are now more looking at string theory and at loop quantum gravity than they did a decade or two ago. But one problem is that David gives well, to some extent he just uncovers what seems to happen in the string community, and to some extent he endorses it, namely that he states that it's more or less okay that mathematical physics gets
He's
more
not
and more
judgmental. He's trying to, I thought he was trying to explain from a point of view of a sociologist or a historian of science or maybe a philosopher of science, why he's trying to understand why these people are functioning the way they do for the last 30 years.
Right. But
Yeah.
also uncovering that parts of mathematical physics get more strongly and strongly divorced from experiment, and why, you know, that it is a weakness that there hasn't been any concrete predictions in parts.
I'm
of
sorry,
mathematical
we must not have read the same book. Have you read the book?
big part of it. Well, but
It's
if
not,
I can say something related, just since you said earlier that it's a pity that there isn't as much dialogue between physicists and philosophers anymore as there was in the 1910s and 20s.
Yes.
And you said that a reason might be that physics has become technically so hard, implying that maybe, well, it's too hard for philosophers, in addition to philosophy, to also keep up with physics. I think, so 10, 20 years ago, it was true that most people, even those who were doing philosophy of physics, focused, for example, on non-relativistic quantum mechanics and just on special and general relativity, but not so much on quantum field theory, let alone quantum gravity, or alternative classical theories of gravity like Teves or other alternative theories. I think that has changed in the last 10 to 20 years. So I think philosophers really are engaging more strongly with these theories too. And if you talk to the right philosopher of physics, I think rather than complaining about the maths getting too hard, they would try to challenge you on providing a bit more mathematical detail on what is the precise mathematical link between the temperature and the area of a black hole. How can you really make that well defined? Or between the idea that you have a classical solution to Einstein's field equations, like a wormhole solution, and that the two ends of the wormhole are supposed to be somehow entangled. How can you make that precise in terms of Hilbert spaces? So that's what I think the right philosopher of physics would try to challenge you on.
You should have come to meeting. We didn't have a time.
Okay. So Eliezer, when is the cutoff? The real cutoff? You told me half an hour ago, but no.
I think there's no real cutoff, but I think I would like Hanoch to give a few minutes to explain the Einstein exhibition. There is food for the hungry, and it would be a nice way to finish, but there is no real cutoff as far as I know.
No, I just see a lull in the, so we can, so Hanoch, so we can, does anyone on the panel want to make any other remarks? Okay. No.
I don't know what Carlo thought of that book.
I read.
But what did you think of it?
Oh, I'm sure I'd like
I think it's exactly the same comment that I think there's a mixture between the. I think there's a bit of confusion between history and philosophy in that book. Or more precise, it is a confusion between a description, what David read in the book, which is a description and try to understand what a community is doing on the one hand, which is a very good enterprise, but I think the book confuses that with a little bit of an essay on philosophy of science and a discussion of pauperism. And the mixture of the two, I think, I dislike precisely because it's a mixture of the two. Instead of saying, look, this is what is happening, is saying, listen, there are possible good, new good standards of scientific validity.
Okay. Let me say one thing. I find it inappropriate to have a discussion about a book which no one except me and Carlo and you have read in this audience. I urge you to read it. I think it's a fascinating book because pauperism, in a way, we all know is a little too narrow explanation of how science works. And string theory, or loop quantum gravity included, the way that theoretical physicists act today is a little, certainly does not fit that model. And I found the book so fascinating because it obviously has a lot of discussion of that's the facts. Then it tries to say, how does this fit into a model of how science works, which I think, you might call sociology. Popper certainly didn't call it sociology, he called it philosophy of science. Aside from over-determinism, the fact that we're more and more constrained by what we know and is well tested, there are many other reasons why we continue to do this. I mean, we're smart people. We don't think we're wasting our lives completely on something which is not going to have many experimental tests, for sure. We know, and that's nothing to do with us or our theories. It has to do with this enormous disparity by 20 orders of magnitude that characterizes the physical universe. We're stuck with that. Why do we persevere? So he gives a bunch of reasons, including overdeterminism, but also including a fact of string theory, which enormously differentiates it, I'm sorry, from loop quantum gravity, which are unanticipated consequences. So when the case of the when asymptotic freedom was discovered, that was a solution to a problem that bugged me for years. How do we explain why quarks don't interact at very short distances? But when that discovery immediately led to a realization that could also explain something else, why you can't pull quarks apart. It wasn't a mathematical proof, but it gave a qualitative understanding, perhaps, which turns out to be correct. Those unanticipated consequences of speculation are what encourage physicists often. They replace experimental verification, and they're happen over and over again in the so-called string theory development. As they happen in general relativity. Those are enormously encouraging. Experiment, and finally, he gives sort of three principles, which I think among string theorists we would all agree encourage us. And the final thing is there's no other game in town. Now, Carlo would argue that there's another game in town. And we're sort of arguing with him as to whether that's a game. Okay? But essentially, there's no other game in town. And the reason these young guys, well, it's true. And the reason these young students aren't going to go off and do something else is that nobody's offering them something which is that qualitatively different, well-defined program in which they can calculate and make a name for themselves. Maybe they should, and we could be wrong. But those are the reasons, and they're not Popperian. And so it's a very interesting book, and I do recommend it to the historians, philosophers, sociologists of science. Okay. So thanks to the panel.
document in the history of science and in the history of general relativity. I don't know if there is any other document which has been analyzed as this one, like a Talmudic text, like a biblical text, every line, every equation, every crossing. The Ricci tensor is there, the Riemann tensor is there, practically the solution of the field equation, the correct one, is already there. He misunderstood something and it took him 3 more years. So we will find it there. There is a beautiful letter from Einstein to Sommerfeld where he admits that until now he ignored mathematics. He did not think that it is very important, but now he has the highest esteem for the role of mathematics. Then we go to the next stage, and this is the drama of November 1915. And I understand that David, in his introductory remarks, mentioned something about that. In November 15, Einstein wrote 4 brief papers which he submitted to the Royal Academy of Science, November 4th, November 11th, Prussian Academy of Science, November 4, November 11, November 18, and finally, November 25, the happy end then. And there you will find the first page of these 4 pages with some remarks, what is essential in each one of them. Following that, he writes, he sits down and writes this beautiful manuscript to which we refer here as the Magna Carta of Physics, in his handwriting, 46 pages. We chose a few of them, making some remarks, what is significant there. After that, there is a story which is not very well known. And that is, there are 5 handwritten pages where he derives everything again from the variational principle. He does not do it in the original manuscript. And therefore, and that is also not, I think that David mentioned it, I was not here, but I heard. The whole manuscript, the whole derivation of general relativity has this constraint, this coordinate condition. The determinant of the metric is -1. Initially, it was a restriction. There he already understood that he can do it without it, but it was a very convenient way to show it. And then he writes 5 pages, and if you look at them, there are numbers of equations. We know that he intended to put it inside, to have it there, that he crosses out the equations. From that, we understand that he wanted to add it at the end. Finally, he doesn't publish it at all. At the end of that year, and there is a whole story about that, and that is displayed in a showcase there. That is, it's a drama. And then he sees that Hilbert and Lorentz do derive everything with the variational principle. He could have done it before, half a year before, so he publishes something. Then he writes a letter to Hermann Weyl, which is also quoted there, a beautiful letter, when he criticizes Hilbert. And he refers to Hilbert's assumption that all matter, the origin of matter is electromagnetic, and he refers to it as a very childish attitude about Hilbert. Then there is a showcase. You see, a day after, November 26, November 28, a few days after that, he writes to his best friends, Thanger, Sommerfeld, and he shares his joy and satisfaction. What I have now achieved, how beautiful it is, and how stupid I was, that I did not realize that the field components are not simple derivatives of the metric. They should be the Christoffel symbols. And he repeats that, and he's very joyful about this success with the Mercury criterion. There is one showcase, and this is a mini drama in this whole story. And this is the correspondence with Karl Schwarzschild. And note, and Karl Schwarzschild writes to him from the front line. He is in the army, and he gives him the first exact solution of the field equations. And Einstein is stunned, and he's surprised, and he's pleased, and he responds with a postcard. The postcard, by the way, is beautiful, because if you look at the address of the postcard, where does he write it to? He writes it to Schwarzschild, and the address is the staff of the battalion this and this on the front there and there, and Schwarzschild, as you know, died a few months after that. And there is a few more, and there is one unique case there, which has no explanations. And when you look at it, it's very pleasing to the eye. Everything there is in Chinese. And that is in Chinese. And let me tell you briefly the story. This is our Chinese connection. It is something that happened this year. It is moving. There was a Chinese member of the Academy, Xu Liangui, a relativist, studied Einstein. He was a dissident. He was forced to be re-educated. He was sent on a farm. And in the evenings, he translated Einstein into Chinese, interpreted Einstein, produced one of the first, already in the 50s, collections of Einstein papers. And he does Einstein the physics, but he uses Einstein in his opposition to the regime. He uses Einstein's arguments for human rights. He has a whole book, which is also displayed here, on how Einstein thinks about the Jewish problem. And it is all in Chinese. And he died recently at the age of 94. It was finally published. It was confiscated, it was published under somebody's name. There is a whole story behind that. His sons decided to give all his personal archives, thousands of pages, to the Hebrew University, to us. Our Chinese scholars tell us, who look at it, that it is an extremely important corpus of documents, important for those who are interested in science in China, in the reception of relativity in China, but even more so on the history of ideas and politics in China in this century. So we still don't know what to do with it. We are planning with Jürgen and his colleagues, because they also have an element of interest in Chinese studies, to form some international group that will also do something with that. So now, before you are evacuated, it seems that the snow is very gentle with us. It's not here yet. I shall be downstairs. I shall be there. If you have any questions about any of the documents there, as you sip your coffee, eat your cookies, wait before to be evacuated, I am there to answer your questions. So thank you.
We want to thank everybody. We want to thank everybody who came.
So, Eliezer, just instructions. There's food for everyone.